All right, James, go ahead.
All right, so I'm James Boggs. I'm a seventh year PhD, working with John, I think his last one. I'll be presenting on my work in visual reasoning in Soar, and particularly towards solving a particular kind of visual puzzle with visual knowledge representations in Soar. So first of all, some very brief motivation. I think it's pretty apparent to all of us why visual reasoning might be useful. There are lots of tasks in the real world that benefit or even strongly require visual reasoning and visual knowledge representations, not just abstractions of symbols. Particular visual knowledge itself is a very useful or necessary tool to solve these problems. So things like putting together IKEA furniture, solving a jigsaw puzzle, even planning how to pack a U-Haul truck, all involve manipulating images in your mind, thinking about how things would look, and doing planning in that way. And enabling this kind of reasoning and knowledge representation in Soar has been the focus of my research basically my entire time here. Over that time, I've extended the spatial visual system a lot. That's what this diagram is, and I'll talk about that more in a bit. And so this general research program that I've been doing is how do we extend Soar to include this visual knowledge and visual reasoning capabilities. This particular presentation is about some of the latest work that I've done. I'll give a brief recap about other stuff just so you can understand where I'm coming from. But this current work is essentially how do we solve this particular sort of toy visual puzzle domain? And also how can we represent objects in Soar and what does that allow us to do? So those are the two primary contributions here. And again, I'll discuss this domain in more detail later. But first, I'm going to talk about that background. So many of us here know what the spatial visual system is, but I don't want to assume everyone does. I think there was a time when lots and lots of talks before mine always discussed the spatial visual system. It appears to be no longer be the case. The spatial visual system, or SVS, as it stands now, is mostly a scene graph. It has nodes and edges, and those nodes are either volumetric concave objects, or convex objects rather, or groups of those objects, and they're related to each other by a 3D transform. There's also in the Soar book, there's some discussion of visual representations in SVS. I don't know if that exists in practice, and there are lots of limits to that particular theoretical representation. I won't go over them here, but it is quite limited. So in practice, that doesn't do much, and also in theory, it's not super powerful. So I've been working to extend the visual part. You can see I have the scene graph, it's in blue because it already exists. But I've also added 3 new visual memories. The first and the predominant one is visual working memory, and I'll dive into that a little bit more in a second. But essentially, it's where visual reasoning happens. It's a little bit analogous to symbolic working memory. It holds various visual representations and transforms on them, which allow you to manipulate them. And it's fully connected to symbolic working memory. The agent can go back and forth and understand what it's doing in visual working memory and symbolic working memory and vice versa. There's also a visual long-term memory, which is essentially analogous to semantic memory. It can store visual representations alongside symbolic keys, and then you can access those representations either by looking up a visual input and trying to get the symbolic representation back, or by giving it a symbolic representation and getting the visual input back. Finally, there's a visual input buffer or the visual perception area. This is very simple, but it's basically just there to keep some separation between the visual representations you're manipulating in visual working memory and the actual inputs that you're getting, and to keep those safe from getting altered. All right, so I'm going to focus in a little bit on visual working memory. That's where most of the work in this talk has gone on. It's a set of nodes and edges, just like a lot of other things in Soar. In this case, these nodes are visual operations or visual operators called VOPs, which can generate and manipulate visual knowledge, and they're chained together so that the output of one can become the input of the other. So for example, you might have a visual operation which generates a visual input, for example, this green triangle, and then you feed that one into another visual operation which rotates at 45 degrees. You'll also make another visual input, and then you can stack them together with this union operation. So you can see these are related to each other in terms of how they are transformed. And they're also tied tightly to symbolic working memory. So that all of these parameters, for example, the 45-degree angle on the rotation operation, are controllable and viewable by the symbolic agent. Also, any outputs, for example, if you have a classification visual operator or if you have something that tries to get how tall the object is. Those are all visible to symbolic working memory, and they're updated every time the input changes. So the agent can like get the symbolic information in real time as what it's seeing transforms and changes. So with this kind of brief background out of the way, I didn't want to spend too much time on it. I'll get to talking about my current work. And the image factory domain is where I'm going to start, because this is the toy problem that I talked about earlier. So the essential objective of this domain, it's based on a game called Shapes, essentially, where you take little shapes and you click them and rotate them and stack them together to make target images. And that's exactly what's going on here. Given some input parts, which are these images, and an output design that you want to make, the agent needs to come up with the right set of machines, which are atomic visual operations, such as rotation and scaling, as well as like combining two images together, which will produce that output design. There are a few types of machines, as I just mentioned, scaling, rotation, stacking. Also, input machines will generate these input parts for you. And it's all of these inputs are images, so it definitely requires the agent to be able to reason about what these things look like and to be able to manipulate those visual representations. Ultimately, the agent should return a graph, which indicates the flow from input machines through various operations, how they get combined, and then this graph is simulated as a factory, and the resulting output is compared to the desired output to see how well the agent did. This is, the high-level idea of the image factory domain. There were some simplifications that I made in this work. It turns out that in the general case, the image factory domain that I just described is quite difficult, sort of almost beyond cutting edge of computer vision right now, particularly when you have two objects of the same color that are merged. It's very difficult for algorithms to disentangle those, either traditional computer vision algorithms or deep learning algorithms. So I made a few simplifications. For one thing, there are only two input images, and they're both unique colors and shapes. There's no color changing machine, and these two rules allow us to just segment the desired output by color so that you can see what two parts you need to do, what two parts you need to manipulate and how they match up. It's also limited factory size, and there's a discretized set of rotation and scaling operations that it can do. Again, just to reduce the search space. So these graphs on the right are example factories. You can see you can see their input machines. They're passed into, this one is a rotation machine, which flips at 180 degrees. This one is a scaling machine, and then they're stacked together. And these stacking machines have XY transforms, which are the relative transform between the top and the bottom. So the goal is for the Soar agent to be able to go from these two input objects and this output object to this in the middle area of how does it get there. In order to do this, the agent does need to understand objects. It needs to have this idea of there are components to this final product. They have unique properties, and they're worth looking at by themselves, not just as part of an image. And so in order to enable this, I developed a very simple handcrafted set of object features and an object representation in SVS, which can take an image and extract all this information and then represent it in visual working memory in terms of these like visual features that you see here, for example, the image and the mask, but also in symbolic working memory in terms of, for example, its color, its height and width, and the angle that it's facing according to a particular metric. And I can use both of these kinds of information, both the symbolic and the visual, in order to guide its search for the right answer. And one of the important aspects is that this is a cross-representational cross-representational form of knowledge. So it does have its feet in both symbolic and visual working memory. At the moment, it is just a handcrafted feature set. The features are here. And that does prove to be a little bit of a problem later. I'll get to that in a second. So the image factory agent, it's a Soar agent, which is relatively simple at the end of the day. A lot of work went into designing the guidance to be effective in terms of how it searches for the proper set of machines. So the first step it does is it gets its input parts and the desired product from the task, and then it chops up the product into its two segments. Just simple color-based segmentation. And then because it knows that there's no color changing, and actually this is not exactly hard coded in, it's actually can read the property of the particular task, and all these tasks happen to have that set to be false. But it does understand that the task doesn't have this possibility, and so it can immediately match, oh, I see this as a cyan input part and a cyan segment. Those two are going to be together somehow. I have to figure out how, but those two are going to be how I get from one to the other. Once it's done that, it looks at these as objects, and so it considers, for example, the height and the width, the angle that it appears to be facing, the number of sides as well, help guide it to decide which, how to like try and match it up. And it starts looking at these ratios or the differences between these properties to help guide it to figure out what should I do next? What should I rotate it? Should I scale it? So in this case, for example, there is a negative 90-degree difference in the angle of these two objects. And their sizes are approximately the same. They both are about 135 to 140. And it knows that the scaling is discretized, right? So it's not going to try and figure out like what is that exact scale. It's like it's probably just a one-to-one scale. And it can look at that negative 90-degree angle and say, all right, well, let's just try a negative 90 rotation. It gets a new part out of it, and then it starts comparing this new part to both the segment. Does it cover the segment completely? Does it explain all the parts of the segment that need to be explained? And also to the product. Is it completely covered by the product? Is it sticking out somewhere weird? You could imagine there might be a triangle out here, that would be bad. And in this process, it can also detect, oh, it's partially obscured, right? You can say like, oh, I'm covered by this product, but I don't cover all the segment. There must be something else going on. And in this case, it would be the red triangle that's obscuring this, right? And so it can store that information, which it uses later to add the final machine, which stacks them together. And then finally, it kind of just does a backwards look through of the machines that it used to get these matches once it's found them all. And it adds those to a factory plan, submits the factory plan, and calls it a day. And then that factory plan is simulated and the resulting image is evaluated. So how does it do? Pretty well. Some caveats. I've tested on 16 images. There's some particular bug that's making it hard to do it really fast on lots of images. So only 16 so far. Of the 16 tasks that I gave it, 10 of them were perfect. It was flawless. The images matched up exactly. 5 of them, I think there was something to do with interpolation issues, because these are the worst differences. These are the ones with the worst similarity scores, and they're basically identical to a human eye. One factory it failed to finish. So I'll talk about that in a second. Besides that factory, everything was like relatively quick, no longer than 700 decision cycles, which is about 35 seconds wall clock on my computer. And it also was almost entirely as good or better than the original factory. There were a number of factories where there were essentially no ops, rotations of 0 or scales of 1 and 1, or rotating a rectangle 180 degrees. And the agent obviously just skipped those, right? It actually was able to improve a lot of the factories. One factory, it actually added an accidental machine, and I'll talk about that too. But first I'll talk about that in line with this failure case. So this is the task in which it kind of fell apart. You can see that it's kind of hard to see on this white background, but there's a yellow irregular polygon here under this green ellipse. This one, it ran about 2,000 decisions. It ended up crashing every time I ran it. Probably memory issues. But the reason that it's really having a hard time here is that this is A, an irregular polygon, and B, it's obscured in a bad way by this ellipse. Ideally, as I just talked about, it uses the bounding box height and width to get these scaling ratios that it wants to try, and it uses this minimum area rectangle to figure out the rotation. In this case, both of those were thrown off, the bounding box by this obscuration over here, and then the minimum area rectangle also kind of fit it weirdly once there was this divot in the polygon. And so it essentially had to resort to exhaustive search. That's also for a similar reason why the factory which made an extra machine, it also had an irregular polygon which was obscured. So it seems like in that case, the heuristics of the agent kind of break down. It starts resorting to brute force, and it ended up actually finding like an accidental correct right answer. It scaled it up big, that gave it the right aspect ratio to figure out how to rotate it, and then scaled it back down to the right size. So future work is make that not happen. Basically two directions to solve this issue. Better source code. Obviously, crashing from memory issues means my source code has a lot of room for optimization. I spent the last week trying to make it run faster, gotten pretty good results. This is pretty much the last issue that I've had with that. Also write more source code, essentially. Add more heuristics, add more guidance, try and bake in some more geometry. This is really tricky. There's a lot of things that I could do here. But the more interesting one to me is to improve the object representations. Rather than adding more information to this handcrafted representation, which actually already has a lot more information than I talked about, that isn't useful because it turned out not to work as well as I hoped. It's also very fragile, right? Like these bounding boxes, they're finicky, and I just showed you they're not great. So what would be better is if we could learn object representations with deep learning that would let us solve this in a more robust way. Maybe regress the affine transform between input parts and product parts. Maybe predict the complete product part from an obscure segment. So if got a corner cut off, you know it's actually a triangle, even though it doesn't look like it. Nuggets and coal. Sorry, I'm a little bit over time here. Nuggets. It more or less worked. Soar can definitely do visual reasoning with SVS2. It requires a lot of good Soar code. I'm sure all of you won't have a problem with that. So excellent. Also, it extends Soar to include images and image manipulation. That could be useful to some people. Ideally, once I defend, I'll have some time. I'll try and get this integrated with the main Soar code base. We'll see how that works out. Also, hopefully this lets me graduate. That'd be good. Whole. Handcrafted object representations are really fragile, and that leads to Soar being really fragile in this case. There was one time where like the bounding box was 1 pixel off. It decided that the resulting image was too big, and it wouldn't match it. It just was like, nope, sorry, you're 1 pixel too big. Bonus coal, using PyTorch and Soar is hard. There's a namespace collision. I'm not going to get into it, but that's not related to this work. I just wanted to mention.